Folks, can I have your attention, please? So, we were talking about shooting the dart into the box, having it swing up. And to do this, we had to analyze it from A to B, then from B to C. Actually, we went from C back to B and then B back to A, because we're going to know how high it swings. Although there's some trickiness in being able to figure that out. I think putting your iPhone on super slow-mo and having a meter stick behind will be one way you can find out how high it swings. And from that height, you work backwards to find the speed with which the dart and the box move off together. And then, that's that speed there, and then we took that speed, and we worked back into the collision problem from B to A, or A to B, and we worked back and found that the velocity, muzzle velocity of the dart, is this relationship here, this equation here, the mass of the dart plus the mass of the box times square root of 2gh, which was that speed with which they leave together, divided by the mass of the dart, and the only variable you need is h. But now we're going to try a different approach. We're going to shoot the dart into a box, and they're going to slide off together. And so we're going to take account of the fact that there's a coefficient of friction between that surface and the block. Now, just like we did up above, we're going to go from A to B where they're together, and then B to C at the very end. And we're going to say that from B to C, energy is conserved. The mechanical energy at B equals the mechanical energy at C. What kind of mechanical energy is there right there when the bullet strikes the back and they start moving off together? There's kinetic energy. So the kinetic energy at B. What type of energy is at C when the box is at rest and it's not moving? Well, there's no potential or kinetic. Where did that kinetic energy go? It went into the work done by friction. What's the formula for kinetic energy? 1/2 m. What mass are we dealing with here? And again, that mass is the mass of the box plus the mass of the dart. Just to be clear on that. Equals, and what's the work done by friction? What's the formula for the work done by friction? Well, it's force of friction times distance, right? And what's force of friction? Anybody remember? What is it? Yeah, mu times normal force. What's normal force? mg times the distance the box slides. Now, the mass here is the same, so what can we do with those masses? Yeah, they cancel. And if we solve this for v, we find that we get what? Square root of 2 mu g d. Mu is the coefficient of friction between the surface. We're going to have to find that. I'll talk about how we can do that. G is gravity. D is the distance the box slides. And this velocity is what? I want to be careful. This is not the speed of the dart. What is that velocity? The speed with which they move off together after the dart hits it. So now, like we did up above here, we need to go back and do from A to B. And what kind of physics concept do we look at from A to B? Well, it's a collision, so what are we going to do? Conservation of what? Yeah, we're going to say the conservation of A equals the conservation of B. Or momentum of A equals the momentum of B. What is the momentum of A? Anybody? Mass of the dart times what? The velocity of the dart. That's what we're ultimately looking for. After they hit and move off together, what is the momentum? Mass of the dart plus mass of the box times what? Well, the velocity they move off together, which we're going to know that from there, right? So now it's just a matter of solving for the velocity of the dart, and you get mass of the dart plus mass of the box times this whole thing, 2 mu gd, all over what? Mass of just the dart. So here is our final equation for this. Now, what data are you going to need to take? You're going to need the mass of the dart, the mass of the box, and the distance they slide off together, right? But there's something else in there we're going to need. Mu. Does anybody remember how we find mu? You can put a box on a surface and then do what to it? Raise it until what? Starts to slide. Theta. Does anybody remember that equation? Yeah, mu equals tan theta. Now that was mu static, and we're wanting mu kinetic. So it's a little different. You're going to want to raise it till it starts to slide and then lower it till it stops, and that's the angle you want. Does that make sense? Because you want the kinetic coefficient, not the static. All right? But that's basically, so we really want mu k. We want the angle not at which the box starts to slide, but at which when we lower it back down, the box stops sliding. All right? So you have to almost do a separate little mini experiment here before you can shoot the bullet into the box. All right, does everybody understand that I'm wanting you to do, for this method 2, one of these two? Everybody okay with that? All right.